Hello student, we're back again with a new topic, and that is Fourier Transform. So we are going to study Fourier Transform under a topic called as integral transforms. And this Fourier Transform is a mathematical tool which we are using in physics to analyze the frequency signals. Now, Fourier transforms, we are using it for frequency analysis of signals. Similarly, we are using Laplace transform for analysis of system and circuits. So these are the two mathematical tools we are using in physics to analyze the signals. Alright. Now, in 1822, J.V. Joseph Fourier, a French mathematician, he explained Fourier series with a famous theorem which stated that the sum of all the sinusoidal harmonic components are relating to a particular type of series, and that series was called as Fourier series. So he said that the Fourier series is used for periodic signals to expand in terms of their harmonics which are sinusoidal to each other. So here we are going to focus on three main words: periodic signals, harmonics and sinusoidal. Now we know the definitions of all these as we have studied it before also in the chapter of waves and oscillations, etc. Right? So what are periodic signals? What is a sinusoidal wave? And what are harmonics? Sinusoidal wave, as you can see in this picture or in this figure, we have a sine wave, right? So these Fourier series we are using for those waves which are sinusoidal to each other, alright? And we are talking about periodic function. Now what are these periodic signals? The signals which repeat at equal intervals of time, they are called as periodic signals. So periodic function, I define it as if value of f of t, that is a function of time, repeats in equal intervals, repeats itself at equal intervals, then I call this function of time as a periodic function, right? So if I want to represent it mathematically, I'm going to write it as f of t is equal to f of t plus or minus t is equal to f of t plus or minus 2t and so on. So if you see, these are the repeated intervals t, 2t and next will be 3t, 4t and so on. So they are repeated, they are repeating itself at equal intervals, t, 2t, 3t, 4t. So the difference is t itself, right? So this t is nothing but the time period. Alright, and along with the time period comes the definition of frequency. Now what is frequency? It is cycles per second, or you can say cycles per time taken. So how many cycles are being repeated in a particular time period, right? So if I take this wave here, I am having one complete cycle, one complete wave, right? So one complete wave is or cycle is completed in the time period t, right? Half of the cycle is being completed in half time period, half of the negative cycle is being completed in another half time period. So totally the time period is t. So if I define frequency as cycles per second, I have one cycle per t seconds. So I define frequency as 1 by t cycles per second, or I call it as 1 by t hertz. Hertz is a SI unit of frequency, right? Now next let's see, what do we mean by harmonics? Harmonics I can define with an equation here. I'm just taking some random equation. Okay, x of t is equals to 2 sine omega t plus sine 2 omega t plus 7 sine 3 omega t plus and so on. So this 7, 2 and 1, they are just, I'm taking it just for the name's sake. But what we are going to focus is on omega t, 2 omega t 3 omega t, and so on. So they are going to get repeated as here we have 1 omega t, 2 omega t, 3 omega t, next will be 4, 5, etc. Right? So what is this representing? Right? So this omega, we all know that it is a fundamental frequency which is equal to 2 pi f. That is the 2 pi times the frequency. Right? Or we can say omega is the angular frequency. Alright? So we have omega to be the fundamental frequency, and sine omega t is the original signal. And this we are calling it as first harmonic. Alright. Now when we move on to the 2 omega t, sine 2 omega t, the 2 omega t is the second harmonic, 3 omega t is the third harmonic. Now what these two represent? They are the integral multiples of the fundamental frequencies. So when we have an integral multiple of the fundamental frequencies, we are calling it as harmonics. And 2 omega, 4 omega, 6 omega and so on, we're calling them as even harmonics, and 3 omega, 5 omega, 7 omega, we're calling them as odd harmonics, right? So whenever we have studied the chapters of waves and oscillations, we have spoken about the periodic functions, we've spoken about the harmonics, we have also spoken about the sinusoidal nature of waves. Alright. Now how are we going to relate them to Fourier transforms? Right. Now the Fourier transforms, they exist for energy signals, pulse signals and impulse related signals. Now when I say energy signals and pulse signals, they are absolutely integrable. Okay. Whereas these impulse related signals, they are not even energy signals nor pulse signals. Okay. And we say that Fourier transform does not exist for non-energy and non-pulse signal. Right? So when we say this, how come we say that the Fourier transform is existing for impulse related signals? That is because of an exception, because these impulse related signals are absolutely integrable. And this is an exception we are going to use where the Fourier transform is existing. So Fourier transform is existing for energy signals, pulse signals and impulse related signals because they are absolutely integrable. Okay, and they do not exist for non-energy and non-pulse signals except for some exceptions which are absolutely integrable. Okay, now we have some conditions for which these Fourier transforms exist. So these conditions, we are calling it as Dirichlet's condition. The Dirichlet's conditions. Now these are the conditions for existence of Fourier series. So we have three conditions here. The first and the second condition are the strongest condition, and the third condition is usually the weakest condition for the existence of Fourier series. So when do we say the Fourier series exists? Okay, the first condition, it says the function has finite number of maxima and minima in each period, right? So when I say maxima and minima, now we have a wave shown here, right? So in this we see that we have a maxima here and a minima here, right? And again we have a maxima here and a minima here. So according to the condition, we should have a finite number of maxima and minima in each period. So this is one time period, that is from 0 to t. So this is one time period and we are having one maxima and one minima in this particular time period. So that means I am able to count or the maxima and minima in the time period t is 1. 1 each. One maxima and one minima. So that means in such a type of signal, in such a type of waveform, there exists Fourier series. Now we have one more figure down here. So if you see here, this is also periodic signal, okay, and we have a time period t. But if you see here, we have a minima here, then maxima, minima, okay, maxima, minima, and so on. So we are unable to count here. So that means this is infinite. We do not have a finite number of maxima and minima in this particular time period. So that means in this particular signal or in this particular waveform, Fourier series does not exist. This is the first condition of existence of Fourier series. Right? Now coming to the second condition. The second condition says the function has finite number of discontinuities in each period. Now here in the first diagram we have a square wave or a rectangular waveform. Okay, now since we have studied in the digital electronics, we have the 1 and 0, the high and the low here. So in these signals, if you see, we have a discontinuity, high and then we have a low, high and then we have a low. So we representing it as 1 and 0. Now in this particular time period t, we have a finite number of discontinuities, that is 1, 2. So we have 2 discontinuities in this particular time period. Okay, and if we continue for the next, we are going to go on, we are able to count or we are able to say that the discontinuities are finite. Okay, so here the Fourier series exists. Right, now coming to the second figure here. If you see this, again we have a rectangular type of waveform, but it is not as simple as it looks in the first figure. Right, so in this time period t, we see that we have 1, 0, 1, 0, 1, 0, 1, 0 and so many discontinuities in the time period t. So we are having again infinite discontinuities in this time period t. So therefore, the Fourier series does not exist in this particular waveform or in this particular signal. Alright, I hope the two conditions are clear. Now let's move on to the third condition and the final condition. The final condition or the third condition. The third condition says the signal should be integrable over a range of period, or I can say the area of the signal has to be finite. Okay, or mathematically if I say integration of f of t dt mod f of t dt over the interval 0 to time period t should be finite. Now what it means? Okay, so let's see the diagrams and let's try to understand what the last condition means. It's a weak Dirichlet's conditions, but still we need to understand this. Alright, so now again I am having a rectangular waveform, and if you see here, I have to find the area and I have to say that this area is finite. So suppose I take this height of this rectangular wave to be A. So what is this? This time period is t by 2. Okay. So the area of this rectangular wave or the half cycle of the rectangular wave in the half time period, we have this to be equal to A into t by 2. The same thing will continue if I go to the next. So that will be A into t. Right. So when I see that A into t or A into t by 2, this is nothing but a finite value. So that means integration of mod of f of t dt over the limits 0 to t is finite. So in this type of waveform or in this type of signal, I can explain the Fourier series, or I can say that Fourier series exists. Alright. Coming to the next diagram, here if you see, the f of t is equal to tan t. So this signal is representing, or the function of time is representing tan of t, tan of the time. Okay. Now if this is the complete time period t, okay, for all the values of t, that is from 0 to pi or 0 to pi by 2 or anything, when I should get the value to be finite so that the Fourier transform exists. But we know that tan pi by 2 is infinity. So for the value of t to be pi by 2, the value of tan t is infinite. So at a particular time t, I am going to get area to be infinite. Right? So that means Fourier series does not exist in this type of a signal. So therefore, in all these three conditions, we are talking about finite and infinite. Finite number of maxima and minima, finite number of discontinuities, finite area. So these are the three conditions for the Fourier series to exist. I hope the Dirichlet's conditions is clear for you all. In this video, we have studied about the introduction of Fourier series and the Dirichlet's conditions. So we have seen how the Fourier series came into existence and the conditions for its existence. Right? So in the next video, we're going to learn more about Fourier series. So if you have liked my video, please subscribe and share it to your friends so that they will be benefited with these videos. Thank you. Hope you have a good day.